Okay. Oh, people can hear me. I shout a lot.
All right. Hello, everyone. Welcome to Midwest Mechanics Seminar. It's my pleasure to introduce Professor Bharath Ganapathisubramani, and he is an expert in experimental fluid mechanics in the Department of Aeronautics and Astronautics at the University of Southampton in UK. He completed his master's and PhD in aerospace engineering at the University of Minnesota and undergraduate degree in naval architecture and ocean engineering at Indian Institute of Technology, Madras. Previously, he was an assistant professor at Imperial College London and then moved to Southampton as an associate professor. He currently serves as an associate editor for Experiments in Fluids and Flow, and he is also a fellow of Royal Aeronautical Society and the American Physical Society, as well as an associate fellow of AIAA. So today he's going to give a seminar on vortex dominated flows. Can't live with them, can't live without them. So really looking forward to the talk.
All right, thank you so much, Anshul. Thank you everyone for being here and for kind of putting up with me the whole day, going to different labs and meeting different people here. Thanks also for the people online for joining. So this title came about because I was talking with my partner, with my wife. Oh, I'm giving this talk and it's around February 15th something. And I said, I want to make this some Valentine's theme type talk. And she said to me, oh, is there something that you really love and hate? And vortices are definitely one of those things. So I'm going to talk about two problems, one where I don't want the vortices and another where I want some vortices to help me achieve the kind of things I want to do. Okay, so the crux of my research actually focuses on primarily sustainable transportation and energy. And within that, there are all these different problems, right? And within all of these different problems, going from urban air mobility to new aircraft concepts to energy, both ocean and wind and solar, or kind of what looks like these wind-assisted propulsion, which seems like we are going back to the age of Vikings, where we now have actually, an A380 size wing now mounted on a tanker or a carrier, which is kind of an interesting concept for improving propulsive techniques. But in all of these problems, we usually have a range of flow, noise, and thermal management issues. And typically, they involve some kind of unsteady aerodynamics or turbulent shear flows. And that's more or less the areas of research that I work on. And there are very many different applications in this. And I'm sort of, if you will, problem agnostic. Things that roughly fall into this category. And if it's interesting, I kind of work on it. So that's how I sort of approach research. And I do it in a very experimental manner in the sense that we make models, put them in our wind tunnel, water tunnel, etc., and then figure out what happens. And I can only do that because at Southampton, we have a Center for Experimental Fluid Mechanics, where we have roughly 2,000 square meters worth of lab space for all kinds of facilities. And it ranges from a boundary layer wind tunnel to an anechoic wind tunnel to towing tanks to large cross-section wind tunnels. We are currently building a refractive index match facility, a water tunnel. So all of these facilities actually enable us to do the kind of work that I show. In addition to this, we have other kinds of small labs. And these 4 labs especially are given a national facility status. So as in other people from other universities can come and use our facilities. And then we kind of share our expertise with them when they want to do kind of these kinds of complex measurements, right? So that's kind of the general ethos. So we have about 10 academic staff who are in this center. And so that's kind of a rare thing where you find 10 experimentalists in one university. So I'm kind of blessed with having those colleagues with whom we share these resources and all the facilities as well. Okay, so today I want to talk about 2 problems. One is flow past porous bluff bodies. And in this case, we want to kind of not have vortices, right? And then I'm going to also talk about flow past multiple flapping foils, where the presence of vortices help the performance of these foils. And they have the same underlying feature in the sense that they're both vortex dominated flows. They have vortices. It's just that in one case, you don't want them. And in the other case, you kind of want them or you need them in order to do the kind of hydrodynamic performance stuff that we want to achieve, right? So the disclaimer here is these two are really kind of established topics. And there are lots of people who've written lots of good papers. Some may even be in this audience. And if you don't see your name in my talk, I'm sorry. If you read the paper, please, you will be potentially properly cited. So I'm just giving you a story from my perspective here. So it's just a fair warning to people who might feel like, oh, he should have cited my work. I'm really sorry about that. Okay, so let's start with flow path bluff bodies. This work was actually funded by our NSF equivalent, which is called Engineering and Physical Sciences Research Council. And the work was primarily done by Murillo, who's a postdoc, and Dan, who's our kind of lab technical officer. And they were assisted by a couple of undergraduate students. But really, the problem was actually proposed by my colleague, who's now retired, Professor Ian Castro, who comes in once a week, just kind of shares a good idea with us and says, what would happen X, and then walks away. And then we all have to pick up the pieces and do things. And then 3 months later, he comes back, hey, I remember I talked to you about something. What's happened to that? And these are some of the results from one of those conversations, right? So, and then it's now actually a very well-funded program, but it just came out of a lunchtime conversation of like, what would happen if ... So I'll keep his picture here because this is pertinent to this introduction. So if you just take a thin flat plate, which is a very typical bluff body, so as in the flow is essentially normal to this flat plate, right? So it's very thin. There are two kind of edges on the two sides where the flow will separate, and then they will have some unsteady shear layer, which will have a separated region, right? And then this is the kind of flow you will see. What you'll see is like a negative vorticity and positive vorticity, and they flap around and they create these vortices that get shed and then released, and then they cause unsteady loading on the object and all kinds of detrimental effects. And if I put a probe, a hot wire probe or any probe really at some point over there, and then I look at the energy, the spectrum of that signal, time series signal, you will get this clear sort of peak that you see here. And it's got a non-dimensional frequency of about 0.15. Okay, so, and that's sort of a universal, what's called a Struhal number, that frequency. And this is the kind of the mean flow field. So if you take a lot of data, time average it, this is the kind of flow field you will get. And there is this clear separation region, and there is a shear layer at the top, shear layer at the bottom. And this separation region essentially prevents if you will, the two shear layers from talking to each other. And at the end of it, they then start to communicate. And then essentially, as this shedding happens, instantaneously, the separation bubble sort of moves up and down. And that's what leads to the load fluctuations on this object. I mean, there are lots and lots of applications for this. And it's kind of obvious. I don't have to state them, where there are thin, long, slender bodies everywhere, which has unsteady loads acting on them. So the reason Ian's picture is pertinent because he did an undergraduate thesis in 1969, right, on this topic. And what he did was he said, okay, I'm going to take that plate and I'm just going to drill a bunch of holes in them. So he made them porous. Okay, so he literally put a lot of holes in this plate and then said, okay, let's see what happens to the flow when you drill all these different holes into that. And he defined a porosity or a value called beta, which is essentially just the open area ratio of the open area divided by the total area of this plate. So essentially how much of it is kind of now got holes in it, and you just divide it by the total area. So when you do that, he found that as beta increases, the wake of that porous plate changes. And he published this in this single author Journal of Fluid Mechanics paper in 1971, all by himself. He said he had one review who said, it's okay. And then the editor chose to publish it anyway. So he said, those were the days where we could write JFM papers easily, not anymore, right? So, I mean, I think he was joking. I don't think he only had one reviewer, but this is what he said to me. So we said, okay, we can do the same sort of thing. So then there are other people who've done this kind of work before. So what I'm now showing is just the coefficient of drag of this plate as you increase the porosity. So at 0, you basically have the solid plate, which has got a drag coefficient of 2. And then as I increase porosity, and obviously if this goes to 1, there is no plate, right? 50% is sort of half the plate, if you will, and then so on. And you see this nice sort of monotonic decrease in drag coefficient as you increase the porosity of this plate. And we did the same measurements with different in wind tunnels and water tunnels, and we basically get the same trend, right? So the interesting thing is this vortex shedding, right? So from this figure, it's sort of not obvious whether a phenomena would exist or not just looking at the drag value, because the drag just has some kind of monotonic change. It doesn't say, well, there'll be vortices here, there won't be vortices there. But Ian in his paper actually found that at around the porosity of, I don't know, 0.22 or something like that, this peak in the Struhal number stopped to exist, as in there was no vortex shedding. Okay, so there were no clear vortices when you have this kind of beyond that open area ratio or beyond that porosity. So he called that region no shedding and that region sort of vortex shedding region. So, but it's kind of doesn't make sense, right? Like, because the drag coefficient clearly shows a monotonic trend, but how can the vortex shedding just bifurcate from yes shedding to no shedding? So this has to be something. There has to be something more to this. In fact, Bierman and Truman, a few years later, what they said was, okay, to figure out what portion of this drag might come from vortex shedding, what they did was they just put a thin, long splitter plate in the wake of this object. And what that does is prevents this shear layer from communicating from that shear layer. And if the two sides of the object cannot communicate with each other, you cannot have vortex shedding. And if that's the case, you will get a different trend, hopefully, for this drag curve, if that was true, right? So they tried to play with that, and they actually did find that below that blue line, if you will, below that porosity, there is clearly a region where the drag comes because there is vortex shedding. This is just a mean drag, mind you. This is not fluctuations. This is just the time average drag. Okay, so the time average drag comes from the fact that there is this unsteady phenomena in that side. And you can do a simple potential flow model, and that will actually, that's this solid line, and it actually captures the same behavior. But a potential flow model that cannot capture is this vortex shedding thing that exists. And you don't even know, you couldn't quite work out how to account for that. So that gray region is the drag induced by this vortex parcel, right? So our hypothesis, talking in this lunch conversation with Ian, was, well, that cannot be a single line, because if this is not going to be, this is not a bifurcating flow where something happens and something doesn't happen. We expect there to be a region where you go from having vortex shedding and not having vortex shedding. And if we can work that out, then we'll be able to tailor engineering devices to actually account for the fact that there is a range and not just a single point that you have to worry about. Right. So the question we had was, what is this region? How do we determine this? And what kind of things can we do in that scenario? So we did a bunch of experiments. We did a wind tunnel experiment and a water tunnel experiment. I mean, those of you who are experimentalists, I can talk to you all day about these figures. So I'm going to skip that and just say, please trust me, we did experiments. And anything colorful that you see, all are experimental data. Okay. So this is experimental data. So what I'm showing here is, as porosity changes, how does the mean flow behind a body changes? So solid, and as porosity increases, what you see is that separation bubble, there's now base bleed, as in the flow goes through the object. And that means that separation bubble actually changes from being there to there to there to there to there. And there doesn't seem to be any bifurcating behavior there either. It's just like a slow transition from the separation bubble existing to not existing at some point. Okay, so then that's kind of the same thing over there. So what we can do now is we can basically put a single hot wire probe, just like Ian did, at that location. And then we can look at spectrum as a function of different porosities. And what you clearly see is that there is certainly, porosity at 0.1%, 0.12, which is 12%. There is a peak at 27%. That peak is significantly diminished. And by 36%, it's not there. Okay. So the relevant length scale actually for this bubble, it turns out, is not really the length of the plate. It's actually the width of that separation bubble. So if you actually scale everything by the width of the separation bubble, you can make all of these Struhal numbers actually collapse, even though there is marginal differences between them, right? Anyway, so there is some weak trend with Reynolds number, and beyond 0.28, we find that there is no peak. So which means there's definitely no vortex shedding beyond that number of 0.28, but we still want to look a little bit more about what happens smaller than that value. Okay, let's explore that further. So what we did was we put yet another probe on the other side, and then we said, okay, so we have two probes on two sides of the shear layer, and if there is vortex shedding, what you should find is there will be a signal on this probe, and then a short time later there will be a signal on that probe, and they will sort of alternate depending upon how periodic your system is, right? So we then looked at the coherence and the phase between those two signals. And what you clearly see is there is a clear coherence, and then there is also its harmonic. And then you can see the coherence happens at a phase difference of 180 degrees, and its harmonic happens at a phase of 0 degrees. So it's very clear that something happens in this very periodic manner in this flow. And this is for the 0.12%. 0.12, which is 12%. So the way I think about this is the first peak in coherence and phase is the evidence of vortex shedding. And the second harmonic, if you will, captures how strong or repeating this shedding really is, right? So that means there is clear time correlation between this happening and that happening in time or in frequency space. If happens, and that's the second harmonic, which happens because there are two of them. So if I now look at the same thing for, say, 0.19%, I still see the same kind of signal. Even though there is base bleed, the separation bubble has changed a little bit, but this idea of vortex shedding still exists. And then as I increase that porosity, it now 24%, only the first peak exists. And if I look at that, you see vortex shedding happens, but not all the time. So if you watch that movie carefully, you'll see sometimes you will see these vortices crossing, but other times they do their own thing. The two shear layers don't seem to talk to each other. They sometimes talk to each other, at other times don't talk to each other. And then if I go to 33%, I don't see anything. I just see the two shear layers doing their own thing. So there's no real relationship between one side of the body to the other side of the body. So this kind of doing random things by themselves. And that's borne out there. So if I actually do a composite, like a regime diagram, in this axis I show porosity, in this axis I show frequency, and what you clearly see is for up to 0.2, you get the first peak and the second peak. And then from 0.2 to about 0.28, I only get the first peak, but not the second peak. And then after 0.28, I get nothing. So from this, what I can say is, well, so there's a region where there is regular vortex shedding, the length scale of which is determined by the size of that separation bubble for that frequency. And then there is a region where there is no vortex shedding, and there is somewhere in between, there is a transitional region from yes vortex shedding to no vortex shedding. So it's not a single line. It's actually a region where it goes from very periodic, repeating, strong events to events that happen some of the time. And when it happens, it's just like, it's like a stochastic system. Sometimes it happens, sometimes it doesn't happen. And then eventually at some porosity, it doesn't happen at all. So all of this stuff is published in this Journal of Fluid Mechanics paper. And if you want more details, you can look at them. And then at that point, Murillo got really interested in this problem and then said, okay, what if we looked at the unsteady loads on this porous plates and then see how they might be related to these vortices that are coming off this. So this is just the mean again. So do we first of all get unsteady forces? And if I look at take a load cell that is actually measuring the forces on this plate, which is there, and then you said, okay, what are the spectrum of that forces experienced by that plate? What we find is for porosity of 0, we get a peak. But once we go to 12% and 16%, you don't see that peak at all, which means the unsteady loads are not transmitted to the surface. Even though there is vortex shedding in these two conditions, the plates themselves don't experience that unsteadiness. They are just seeing the mean drag, and that's it, which is great, right? If you're thinking about flow control, reducing the loading on an object, just a little bit of porosity, 10%, might actually do the job, and then you can remove a lot of the unsteady load and get a reduction in the mean load as well, because that also decreases, right? And then you get the benefit of having the mean reduction and the unsteady reduction, right? So if I look at the 3D flow field, why does this happen? You can kind of clearly see you have very coherent vortex shedding for beta equals 0, and you can look at this look at this region of vortices, and then you find how coherent is it across the different span-wise locations of this plate. And the red region basically shows strong coherence. And so what that says is, if I have a solid plate, you get vortex shedding everywhere along the edges of the plate, all along the span. Okay, so there's a strong span-wise coherence in the near wake. But the moment I put some porosity, what happens is it just sort of phase scrambles them across the two sides. So as in, sometimes there's vortex shedding here, at other times it's here, at other times it's there. So when you average over the whole plate, they all these fluctuations sort of average out, and you don't get any of this thing at the integrated sort of plate size level. So you can see the coherence now at the base of the plate is completely sort of removed, and you get a near field span-wise coherence, which actually decreases with increasing porosity. And then the question was, okay, now let's make it free to rotate, right? So it's no longer just sitting there. Now we can kind of rotate. So we just add a torsional spring, and then say, okay, do you rotate under the influence of vortex shedding or not? Okay, so we know now putting holes reduces mean drag. It also reduces unfluctuating drag. But even though vortex shedding exists, okay, now if you let it free to rotate, the question is, will it keep rotating? Because a solid plate would. And at what porosity will the rotation actually stop? Because we want to know at what point these vortices don't have any effect, if you will, on the object itself. So we basically built a system where you can just essentially let it free to rotate with a spring there. And then this is the kind of thing it does. At 4% porosity, you can see, and this is not active, right? It's just doing its own thing. It's a fully passive aeroelastic or hydroelastic system, right? So then it does that at 4%, and I increase porosity, and at some high porosity, the plate just reorients itself in its minimum drag position, which is along the flow, and then just stays like that, right? So the question is, where would this happen? So what we did was we just measured the amplitude of this rotational angle, and then just plot that as a function of the porosity of this plate. So we can do that, and here's what it looks like. And we did that for different reduced frequencies or velocity ratio, depending. You can define them in different ways. It's just a relationship between speed and size compared to the natural frequency of the system. And what it shows is up to 10%, there's vortex-induced vibrations. And beyond 10%, there is nothing. And it's just like that. It's abrupt. Right? So just like literally some kind of bifurcation or something is happening where it stops from doing oscillations and not doing oscillations. And that's the line there. So there's that threshold. And the question is why? Why would you have this threshold? Right? So then we started taking some measurements of the plates just at a fixed angle of attack and then not moving. So we just fixed the angle of attack, and we said, okay, something has to be happening to the center of pressure of this kind of thing for that behavior to happen. So we try to do some kind of pressure from PIV and these kinds of fancy things. And then, we realize, okay, we have our own limitations to worry about. But regardless, the hypothesis is as follows. And we are currently doing some measurements to confirm this hypothesis. So when you have 0% porosity, your center of pressure it's basically like a flat plate airfoil. So the center of pressure is somewhere near the quarter chord or somewhere there upstream, okay? Now, as you add porosity, you can look at the flow field. You can convince yourself, if you squint at it long enough, like we have, that that center of pressure is actually moving a little bit further down. And then as you go more, it moves even further. And we believe at 10%, the center of pressure actually moves just to the other side of the rotation axis. So when that happens, there is no restoring force. So it just goes to its equilibrium position and or stable position and just stays there. Okay, so this is kind of what is happening here, where like when you let it free to rotate, you kind of have to, by changing the porosity and the flow field, you can change the center of pressure, which helps you alleviate any vortex-induced vibrations. Okay, so beyond that, what are we doing? Currently, we are doing this for 3D porous bodies. So here are kind of 3D bodies with lots of different porosity. And you can see how in 3 dimensions, this problem might change. Instead of a thin flat plate, we've also got a finite patch. This is more to mimic a cluster of trees in a forest. And then we get the same kind of effect where like there are vortex-induced vibrations on one condition and not so much on the other ones. We are also looking at what the source of this mechanism is, which is basically the pressure footprint. And that's going to take some time for us to work out. We're doing this with data assimilation. And then finally, we are building a refractive index match facility, as I just said, which allows us to look inside this porous body to see what the flow field is and how that might change the physics of the flow. And that's something we are currently working on. So that's my can't live with them. Let me see for time. I have 20 minutes or so, right? Ish. Okay. So I'll move over to the can't live without them. So this is probably unusual for some of you. So the work actually was funded by Office of Naval Research as well as our UKRI. The work itself was done by Luke Muscat and Rodrigo, who's actually in the audience here. He's a postdoc in Naval Architecture Department. And then I have collaborators who are paleontologists, who are Gareth Dyke and Colin Palmer, and it'll be clear why paleontologists in a minute. And then my partner in crime on this is Gabe Weymouth at TU, who was at Southampton, who's now in TU Delft, where he does numerical simulations of this problem. So some of the colorful videos you will see are numerical simulations. Okay, so so the motivation for this problem starts about 100 million years ago. In what's called the Mesozoic era, where it was, an age of abundance for dinosaurs, right? So at the time of dinosaurs, there used to be these animals called, this whole species called Plesiosauria, which lived in water. And plesiosaur, and there are many different types of plesiosaur within Plesiosauria. Especially, there is an animal. So these are marine reptiles. They're highly successful. They're very long-lived. And they have very long, as in large, as in they're 10 meters or so. They're secondarily aquatic, which means they have to come out, breathe, go back, and swim. And they're air-breathing swimmers. But the unique thing from a hydrodynamic standpoint is the fossil records show that they have 4 very large flippers. Okay, so what that means is they're if you look at their skeleton, it looks something like this, right? There are 4 flippers, like, 2 on each side. So the question was, are there any hydrodynamic benefits to having 4 flippers like this, purely from a paleontology perspective, right? I'm an engineer. I know why it might be useful, but they didn't, right? So they said, oh, do you want to collaborate with us on this? And we were like, sure, why not? So we did that, right? So then we were looking for kind of funding. And then Gabe said, you know what we could do? He said, this is the current underwater vehicle regime, range of things that are available in the world. And these are reasonably expensive. So he said, maybe we should propose something that is sort of plesiosaur inspired, where we say we'll make them slightly more efficient and maybe more maneuverable than these kinds of things that exist. So that was, if you will, our engineering pitch towards solving a paleontology problem, right? So we wanted to build these plesiosaur-inspired underwater vehicles, right? I mean, I don't know who would buy this. ONR bought it at the time. So, I mean, it was great, actually. So it was and you'll see why. Okay, so what we do is we do a bunch of integrated simulations, informed experiments, and modeling So simulations are done using the CFD tool called LilyPad. It's an immerse boundary solver. Gabe's got all the details in those papers. I think now he's got a Julia version of this called Water Lily. So if you're interested, please have a look. And then we did our experiments in the water channel where we built a tandem flapparatus, which basically flaps two sets of wings in whatever kind of things we want. And then, we can play around and measure forces and things like that. So the specimen, we were specifically interested in this thing called the Collard specimen, which is a juvenile, I don't know what juvenile actually means anymore. So I know it means a certain age range, but I don't know what that means in the context of this plesiosaur. So what we had is we actually looked at one of the flippers of this thing. We X-ray scanned it, right? And then that's the kind of fossil it looks like. But the question is, how much soft tissue would go around this particular animal? Because we have no idea, we just have the skeleton, right? So we asked the paleontologists, what would you do? They said, oh, let's look at some extant animals and see what happens. And we looked at the sea lion, we looked at the turtle, we looked at a penguin, and they all kind of have slightly different things where what we were thinking was, okay, maybe if we looked at how much soft tissue is there in front of the leading edge and how much soft tissue is there, behind the trailing edge, maybe we can make some educated guesses about what this plesiosaur would have looked like. And then obviously these three things look very different. So Luke, my PhD student at the time, said okay, what do we do? And then as engineers, we just averaged it, right? So we basically took every span-wise position across all three of them, normalized them by the span length. And then we said, okay, at every span length, we have an average of that soft tissue and that soft tissue, and then just added it to this much to the fossil. Okay, so we scaled everything by the fossil, first the bone size, and then by the span length, and you can basically get everything non-dimensional and then go from there. It's just geometric scaling, really. It's not, but average geometric scaling, right? So we did that, and that's what a plesiosaur flipper would have looked like. Then we needed to get a cross section. So Luke, once again, he looked at an image of this thing from the end, and he saw, okay, that might look like a hydrofoil, right? And then we now already know how much soft tissue has to go there and soft tissue go here. So we again stared at this for quite a bit of time. And then Luke said, that's an Epler foil section, right? So that's the answer, right? So we just put an Epler foil section there. And between this Epler foil section and that plan form, we can now essentially add them together and get a 3D printed foil. So I want to be clear here. When I say soft tissue, I don't mean flexible or anything. I just literally mean how much muscle / skin were there. So I'm assuming for my purposes, they're all rigid. Okay, there's nothing that is flexibly moving. It's just, I just don't know how much it was. This is how much it was. And that's what a foil would look like. And then we looked at how much motion would be there in its hip joint and shoulder joints to see how, if it would flap, what kind of flapping would it do? And so by just looking at the joint, and we went to the Natural History Museum to actually do this, and we found out that it's mostly sort of dorsal ventral, which means going up and down a lot more than doing this kind of thing. So it's sort of essentially, rotating around the hinge of your shoulder or your hip. Okay, so that's what it was doing. So that's what we think a plesiosaur would have basically flapped around like. And then for me, that's just a heaving pitching wing. Once you're in the heaving pitching world, then I'm in business, right? Till now, I had no idea what I was talking about. I mean, even now, I'm not so sure. But here, I actually can build a setup or run some simulations and actually get some answers, right? So that's what we did. So it's a tandem heaving pitching foil motion. So that's the kind of thing it does. So you have a heave motion and a pitch motion. You have a phase difference between heave and pitch. And now we are in the world we sort of understand. Okay, so we know that the amplitude of motion has to be roughly 2 chord lengths, and that comes from the fossil anatomy. And all of these other numbers just come from doing a literature review on flapping foils that have existed for a long, long time before we thought about plesiosaurs. So we just said, okay, let's take the best of all of these words. Let's couple that with the one information we can put into this problem. And now we have the only other thing, I mean, actually, I can take all of these numbers and make them non-dimensional and get one non-dimensional number. So those of you who are interested in scaling laws, you might be interested in looking at this, where we actually were able to collapse multiple different non-dimensional numbers into one non-dimensional number. But that doesn't help us for a plesiosaur. It's just a thing that we did for fun, right? So anyway, so what we can do now is add a second foil, which is what a plesiosaur would have done. And then we said, okay, there is a spacing between them. So let's keep the second foil exactly the same kinematics of the front foil, because that's the simplest thing we can think of. Then at least the plesiosaur doesn't have to think about it, right? And then we said, okay, just add a phase difference between the two sets of foils, as in, do I go up and down together or do I go slightly differently? And that depends, I would assume, on what the spacing should be. So now we have in a 2-parameter problem, which basically gives you a spacing phase difference relationship, and we want to know what is this relationship between spacing and phase difference for these tandem flapping foils. So if you actually do a single foil and a flapping foil, and you look at the wake in a time average sense, you get this kind of bifurcated jet. And the bifurcated jet basically tells you you're producing thrust, okay? And if you do the same with the flapping foil, the tandem flapping foil, the jet is no longer as bifurcated. And in fact, it's more focused and it's more intense. By just looking at this two flow field, you should be able to intuitively guess that this is going to produce more thrust than that one is. Okay, so, and that's kind of what we find. So if you actually take the ratio of the thrust produced by the hind foil to the thrust produced by a single foil or front foil, and then you say that number is equal to 1, they produce equal amount of thrust. If that number is greater than 1, the back foil is producing a lot more thrust. And if that number is less than 1, the back foil is not doing so good, right? So you get these curves of Brzezinski's diagram of phase to spacing, where red shows a lot more thrust, blue actually shows drag, as in it's the back foil is not producing thrust, it's producing drag. And you can get as much as twice as much thrust in the back foil, which means for the whole system, it's about a 50% increase in the thrust for when they actually flap at the right kinematics, right? So then you can say, okay, so, but the optimal phase difference that you need to achieve that is a different value for different spacing. So depending upon, how far away your foils are, you get a different number. And you change the frequency or the Strouhal number, all of that pattern just changes, right? So you will get a different optimal for the same spacing if you flap at a different frequency, right? So, and you can actually predict this behavior by just a simple, so this is the actual data for a Strouhal number of 0.4. And then if I just do a simple quasi-steady model where I just say, what is my CL? It's just, and you project that lift to thrust, and the CL, I'm just doing 2 pi alpha, which is just thin air foil theory. And I get contours that look pretty similar to the simulation data contours, right? So what that tells me is I'm able to predict this tandem behavior with just simple aerodynamics, right? In fact, I can go a bit further and then do a slightly more complicated with sort of circulatory and added mass, which is an unsteady model, and that match gets better. So I can actually, once again, use simple models to be able to predict this and compare that to experimental data, right? So the unsteady model works well, but obviously one thing I'll say is all of these models get worse as you flap at faster and faster frequency. So we are actually now working on corrections to these models to improve this predictions. So then the question is, okay, that's what simulations and our models say. Because I'm an experimentalist, I have to kind of have a plug-in there for do experiments show the same thing. And we just took sort of one spacing of 3 chord lengths, and that's because it's relevant to this particular animal. So that spacing is about 3 chord lengths. So we said, okay, let's go with that one and then see what the measurements show. And what you say, these are 2 different pitch maximum angles of attack. That's what the 2 lines are. What you clearly see is at a given phase difference, at some phase difference, you get maybe 80% as much thrust as a single foil flapping, right? So if you want, the experiment said, the simulation said 2, whereas it's 1.8. Okay, so it's kind of thereabouts. Not only that, So you get that number, but in the same region, you are also more efficient. So you have to put less energy and actually get more thrust when you're operating in that region, which is a massive win, right? Like, and that's not always obvious. So we then hypothesized what a plesiosaur would have done is done that so that they can either chase a prey or escape from a predator, depending upon what it was trying to do at any given time, right? So the efficiency and thrust enhancement happens at the same time. So then the obvious thing is, let's look at what happens, right? So this is from the experiments. It's like, you don't have to necessarily be an engineer to actually think of this through, but you can see when it's doing badly, the back foil just hits the vortex coming from the front foil, and that's not good. So it's just scattering a lot of energy that should not have been used in some meaningful way. And then for the front, when the thrust enhancement happens, it's at a different phase difference. And you can see what happens is the back foil essentially rides between the vortices, which means the circulation coming from those near passes of those vortices actually increases the lift produced by one of these foils, which then gets directed towards thrust. So you get this really nice benefit of operating in this manner. So this is all published in some journals. So then I have to put in a customary, do I have time slide, depending upon where we are. So I have, how long do I have till? 5 minutes? Okay, I'll go to the, Rodrigo, I'm sorry. Okay, because I was going to present some of Rodrigo's stuff, but because I'm running out of time, I'm going to go to my why ONR funded this project, because I think that's fun. So the reason ONR funded this project was we said we are going to make this plesiosaur-inspired thing, and Rodrigo did a lot of work I could have shown, but I wanted to show this thing where we built this underwater vehicle, which actually has tandem flapping foils, right? And it can kind of do the kind of things that traditional underwater vehicles can do, but it can do more, right? So what it can do is it's fully autonomous, obviously. It's got a cruise speed of around 0.6 meters per second. It's got if you put it in biological terms, it's 0.7 body lengths per second. For an underwater animal, that's pretty good. Like if you're a shark, you're going like 3, 4, but we are not looking for that. We are going for roughly 1 body length per second is actually a pretty good performance, right? It's incredibly maneuverable. So it can turn around on the spot. By just changing one side to other side, we can make it just go turn around circles, right? A standard underwater vehicle can't do that because they're all just scaled down submarines. And you have to kind of do a turning radius of whatever it needs to be to actually make this happen. Whereas this, you can. And we think this is what a plesiosaur would have done, but we are probably smarter than plesiosaurs, so maybe a bit more than what plesiosaurs would have done, okay? Or we think so anyway. So we've got this thing, and now that we've got this thing, we can do all kinds of data-driven stuff with this, right? Like, so this is where what Rodrigo does come into play. So we were playing with how do you make it go from one state to another state and trying to apply all kinds of machine learning algorithms to actually try and change the way we operate this thing. So that's sort of ongoing work really right now. And one final thing, so this plesiosaur has appeared in Attenborough and the Giant Sea Monster show in BBC. So this is actually on BBC. It's actually on Netflix in the US, I think. And if you have not seen this, that is Luke Muscat, who was the PhD student. So he's talking to David Attenborough. And he is very, very interested in outreach. So he built a plesiosaur called Flip. And he's got a GoFundMe for him to basically take it around to different schools and actually just get children excited in science and engineering by getting them through dinosaurs rather than other ways, right? So it's kind of I think it's a cool thing. And I don't know, I do everything I can to support Luke in his mission here. So beyond plesiosaurs, this is Rodrigo's work, so we're trying to do maneuvers where we want to go from one type of swimming to another type of swimming using these tandem flapping foils. and we are using data-driven techniques to develop strategies for that. We're doing burst and coast strategies. We're also working on some sensor fusion where we want to do this thing where we want to detect a vortex gust and then do maneuvers based on what's happening in here. And then we are also doing things like flapping foils at very high Reynolds numbers, because ultimately, if Navy wants to put something, in one of their machines, you want this to work at Reynolds number of 1 million, not a Reynolds number of 100,000. So we need to still have an order of magnitude to go, but we are working towards doing that. And we are also doing this in the presence of background disturbances to see how these kinds of techniques might work. Okay, so to summarize, I had two problems. One was on vortex shedding of porous plates, and then I had a bunch of conclusions for it. And then flow past multiple flapping foils as well, where we built a plesiosaur-inspired robot, and we also understood some of the mechanisms of how plesiosaurs could have done its swimming or living. So that's my vortex-dominated flows, and I'm happy to take questions.
A very nice presentation, as always.
Yeah, thank you.
Can you tell us more about the data-driven methods?
I can do, thank you. We can take 2 minutes to actually show you a slide. So all we did here actually was, we really just developed a simple linear model, but it's, I can put it up. Yeah, okay, good. So all we did was we developed just an ODE where we want to make the force as a function of some known state and some control variables, right? So it's just like standard control theory stuff. And then all we did was we used lasso, we used Cindy, but really not Cindy. We just used the Cindy for the lasso. And then we had kinematics inputs. And if you put kinematic inputs, we wanted to see how it would predict the forces, the force history, and it's not so good. But what we actually did was, and that's with just the kinematic inputs, and then Rodrigo called this physics-infused lasso, I think. So what we did was we just gave the locations of these vortices, and then we said, okay, given these locations of vortices, can you now predict this force history? And what it was able to do was actually really do much better than that, right? So that's where it is. But I currently have a student trying to implement this with reinforcement learning, right? That's like the obvious thing, right? Like, Rodrigo wanted to do that, but the problem was we had to run hundreds of thousands of experiments for reinforcement learning to kind of be valuable. So that's actually why we started developing this surrogate model, because then we can run this surrogate model thousands of times and do reinforcement learning. But even without reinforcement learning, I kind of don't have the detail. I don't want to go through the full detail here, but what Rodrigo was able to do actually was just use a genetic optimization without reinforcement learning or anything, and then just optimize the kinematics, where one was very power consuming, whereas this optimized kinematics doesn't consume almost any power to do the same maneuver. So that's the kind of thing we can do. But this is entirely sort of surrogate model driven, but validated with experiments. So as in, we trained the model, if you will, or find the optimal with surrogate models, and applied that optimal kinematics in an experiment, and no change.
May I ask a follow-up?
Yeah.
You need to know the locations of the vortices as an input.
So right now, it's in that Cindy model. But what we wanted to do was have a pressure sensor on the body to see if we can predict that. But that's where we got tricky. Yeah.
Generative AI models to sense what the surface.
Yeah.
Because the follow-up is, what if it's not just vortices, but any important structure?
You are absolutely right. So the vortices stuff is just like a hypothesis at this point, right? But it sort of works. Yeah, absolutely. So we need to kind of work out how to, we can do SHAP. We can, some of those things to see how to detect this importance. But so far we haven't, we just sort of left it here, right? Yeah.
It's very impressive. It's very cool.
Oh, thanks.
Nice.
Thank you. Yeah. Mirko? Yeah.
Since you're in an aerovascular department,
Yeah.
how are you going to do you have any ideas of taking the dinosaur flips? I forgot the name of the guy now, for aero application?
So yeah, we have. So we're trying to do formation flying, and that's a little bit different. But there, the sensing problem is much harder. So we've been trying to play with getting 4 UAVs to formation flies really close to each other. But by just looking at with visual recognition where the front aircraft is, and then positioning the rear aircraft to actually take advantage of some of these things. But the problem is it's right now more of a, so it works in paper. Right now we are struggling, if you will, with the experimental side of things. I mean, so that's where the struggle currently is. But I think conceptually I have no issues with saying this will work. It's just, can I practically get my
As you say, formation flight, since you're the Midwest, geese come to mind.
Yeah.
Which have a different unsteady dynamics. That formation flight has a different unsteady dynamic.
Correct. Yeah. So you can. So what we wanted to do was whether to see whether this kind of approach would work in a just fixed wing UAV, but this thing will definitely also work in a flapping type structure, right? But there's no point in flapping something that size. You probably want to flap things that are kind of that size because the efficiency goes down dramatically as you change scale of this thing. But the idea was we wanted to do fixed wing, unpiloted things just to see whether we can get whether some of the modeling and methods based thing, whether that would work. Yeah, sure.
Thanks for a super cool presentation. Thank you. I was going to suggest it's not lunch discussion here, but maybe you can come up with some ideas to do some more work there. When we did the study of an isolated flapping foil, we found out if you can, well, not the foil, but the wing, that if you allow for flexibility and you have the right amount, you can capture the vortex for longer and you improve the efficiency of that.
The isolated one.
The oscillator.
Yeah.
I wonder what you could do now with 2 of those.
So
At what level? Because these things, they work flexible at some level. You just don't know what they are.
Exactly.
But now, from an engineering point of view, you could play with that.
No, absolutely.
Yeah,
So
interesting problem to address.
yeah, so our problem, you're right, but I think there is also like a ceiling to this problem, because the more you extract on self, the less you have available for the rear, right? So there must be like a happy medium somewhere there, if you will, that you let some energy go and let the back recover some of that. Because we've also done 2, 3, 4, 5, many. It starts to level off after a certain number in terms of what you can recover from the vorticity that's there in the previous foil.
Okay, so then comes the next part, which is don't make all of them the same.
Yeah, you can make them different sizes. Yeah, absolutely. Yeah, that's it.
It's really rich.
Yeah, it is indeed. Sorry, yeah.
Yeah, I was wondering, what is the geometry difference? Sorry, what is how is the geometry of the isolated foil and the dual foil compares? Is the isolated foil have the same total coordinates as the dual foil? The same.
So we've done all these different. So you can take essentially a single flipper, double the essentially surface area, and doing the same thing, you still get much less than having 2. So if you take the total, say, planform area as a constant, you can either put it in one flipper or you can split them and put it in 2 flippers. The 2 flippers works much better, right? So that's why we say, when we say more efficient, that's what we are saying, really. Yeah.
Yep.
Sorry, yeah. Good.
Well, thank you for the presentation. Actually, I have like 2 quick questions. First of all, is like about the cruise flat plates or like flat bodies. There's any standard to drill through those holes, or there's any effect on the side?
Yeah, so the obvious thing to do is to put the holes towards the ends and keep the center a little bit clean, and that will do basically the same thing. We didn't want to get into the like a geometric optimization of this problem, so we just said we keep the same holes everywhere just to get the basic physics. But yeah, of course, you can localize these holes and you get slightly different effects.
Yeah, so I was thinking like, to generalize about the beta parameter. You
Yeah.
can have like different betas.
Yeah, there is a beta, typically should be sort of patient dependent beta. And then there's an average beta, right? Like, we are engineers, we can make this complicated.
And the second maybe is like more out of the box.
Yeah.
It's about like leaving with and without them because
Yeah.
I mean maybe there's also the idea of having a porous airfoils and having the best of both, you know.
Yeah, you could do. You're right. So I could have a porous flapping foil. You're absolutely right, and that just makes my life even more complicated. Or not mine. My next PhD student.
Let's select one more question.
You mentioned that part of Rodrigo's work is to make more efficient maneuvering, but is the current model able to maneuver in complex ways? Because we just kind of saw rotation and moving forward.
Yeah.
But is it stable if you give it some kind of a complicated?
So I didn't talk about stability at all for that reason. So stability is a massive. So in Luke Muscat's PhD thesis, we actually did a flight dynamics model. I mean, I don't know what the hydrodynamic equivalent. I mean, hydrodynamic model, right? So where we actually take all the force vectors and actually assume a center of mass, point mass model, and then we can actually predict the trajectory evolution of this animal. And so it turns out it's also stable when it actually is producing kind of the right forces in the right places. So, I mean, it does sort of go up and down a little, but which you may not have seen in some of those videos, but it's remarkably keeps its station. And when you turn, obviously it starts to sink. But the thing in an underwater vehicle is you have ballast and you can sort of play with other things to keep you there. In an aircraft, it's a different matter altogether, I think. So we can certainly include moments and other things as potential ways to further kind of optimize or improve this problem.
So we are out of time, so I will ask my last question. So plesiosaur, what kind of environment did they evolve in? So what was the Reynolds number and why did they go extinct?
So I was so happy nobody asked me this question, right? And then you ruined it. But okay, so the scale of the plesiosaur is up to 10 meters, right? So the Reynolds number would have been up to 1 million. So they definitely, if they existed, and if these results are to be believed, if you will, they would have flapped and done something. Now, why did they go extinct had nothing to do with hydrodynamics. I think it was some other event which made them all extinct, right? So they were really top of the food chain. They were an apex predator. So I think if you watch that Attenborough show, they actually address some of these things about extinction and so on. But they are actually very
end of Mesozoic is the asteroid. So
yeah, that's right. So it's the some K whatever event, something. So
Time is up, and let's thank our speaker again.
thank you.